Hey, welcome back. So, we've gotten pretty comfortable with the idea of the electric force between two charges. Simple enough, right? But what happens when the party gets a little more crowded? What if we throw in a third charge, or a fourth, or a whole bunch of them? How do all those individual pushes and pulls actually add up? Well, that's exactly what we're going to unravel today. So let's jump right in. We're going to start with a quick refresher on the simple two-charge problem. Then, we'll introduce this one incredibly powerful principle that lets us solve pretty much any multi-charge system. After that, we'll put it to the test with a couple of really great examples, and finally, we'll wrap up with the key formulas you'll definitely want to have in your back pocket. Okay, so before we can even think about juggling a whole system of charges, we have to be absolutely crystal clear on what happens when there are just two. We've got to nail the basics first. And at the very heart of all this is one fundamental rule, Coulomb's law. This is our foundation. This law perfectly describes the force between any two charges, whether it's two positives pushing each other apart or a positive and a negative pulling each other together. And this, right here, this is the big question for today. Coulomb's law is specifically defined for a pair of charges. So how in the world do we handle a system with charges Q1, Q2, Q3, and so on? Is Coulomb's law even enough to solve this puzzle? Well, the answer is yes, but we need one more crucial piece to make it all work. And that beautifully simple idea is called the principle of superposition. Honestly, this is the key. This is what unlocks our ability to figure out the forces in any system of charges, no matter how complicated it looks.
So here's what it says, and it's actually pretty straightforward. To find the total force on any single charge, you just calculate the force on it from every other charge one by one, almost like the others don't even exist. Then you just add all those individual force vectors together. And the most important part? The force between charge A and charge B doesn't change one bit just because charge C shows up nearby. They all act independently.
This diagram shows it perfectly. Just look at that charge Q1. To get the total force on it, we first pretend Q3 isn't there, and we just calculate the force from Q2. That's the vector labeled F12. Then, we pretend Q2 isn't there, and we calculate the force from Q3. That's F13. The final net force on Q1, which is F1, is what you get when you add those two vectors. You can just imagine picking up one arrow and placing its tail at the tip of the other. The final answer is the arrow that connects the start to the finish. That's what we mean by a vector sum. And what's really cool is that this scales up perfectly. It doesn't matter if you have 3 charges or 3,000. The process is always the same. Calculate each force individually, then add them all up. But, and this is super important, we're adding vectors. You can't just add the numbers. Vectors have both a magnitude and a direction, and that direction is absolutely crucial. All right, enough theory. Theory is great, but let's see this principle actually work. For our first example, we're going to use a really clean, perfectly symmetrical setup. Okay, so here's the scenario. We've got 3 identical positive charges, little q, and they're placed right at the corners of a perfect equilateral triangle. Then we take another positive charge, big Q, and we put it right in the geometric center, the centroid. So the question is, what is the total electric force that this central charge is feeling? So how do we solve this? Easy. We just follow our blueprint, the superposition principle. Step 1. We find the force that charge A exerts on Q. Step 2, the force from B on Q. And step 3, the force from C on Q. Once we have those 3 force vectors, we just add them all up. Now, this is where the geometry really helps us out. Because it's an equilateral triangle, the distance from each of those corner charges to the center is exactly the same. And since the corner charges are all identical, that means the strength, the magnitude, of all 3 forces has to be equal. They're all pushing on Q with the same amount of oomph. And because of the geometry, they'll all be pointing outwards exactly 120 degrees apart from each other. And what happens when you have 3 equal forces pulling in opposite directions, 120 degrees apart? Well, it's just a perfect 3-way tug-of-war where nobody wins. They completely cancel each other out. The net force on that central charge Q is a big fat 0. It doesn't feel any push or pull at all. Pretty neat, right? Okay, that last result was cool, but it relied on everything being perfectly symmetrical. So what happens when we break that symmetry? Let's try a more complex case, where we mix things up with both positive and negative charges, which means we'll have both attractive and repulsive forces in the same problem.
So here's the new setup. We still have our equilateral triangle, but this time we have two positive charges at corners A and B, and one negative charge down at corner C. Now the question is a little broader. What's the net force on each of these three charges?
Let's just focus on the charge up at corner A for a second. It's feeling two different forces, right? The positive charge over at B is pushing it away. That's a repulsive force. But at the same time, the negative charge down at C is pulling it closer. That's an attractive force. So we have two forces of the exact same strength acting on charge A, but in totally different directions. And here's the beautiful thing. Even with this new layer of complexity, our method doesn't change at all. That's the power of the superposition principle. For each one of the three charges, we just calculate the individual forces from the other two, and then we do our vector addition to find the total resultant force. The process is exactly the same.
Now here's something really fascinating. If you actually go through and calculate the total net force on A, and the total net force on B, and the total net force on C, and then you add those three resulting force vectors together, guess what? They sum to zero. And this is not a coincidence. This is a direct consequence of Newton's third law. Since there are no outside forces pushing on our little system, all the internal forces, all the pushes and pulls between the charges themselves, they all have to cancel each other out perfectly.
Okay, so when you boil it all down, we've really only used two fundamental ideas to solve everything we looked at today. Let's just put them side by side so it's super clear. And there they are. You've got Coulomb's law, which is our tool for calculating the force between any single pair of charges. And right below it, you've got the superposition principle, which is our method for combining all of those individual forces into one total net force. Master these two, and you can figure out the forces in any system of static charges. So everything we've talked about today assumes our charges are just hanging out in a vacuum. But what if they weren't? What if this whole system was sitting inside a material, like, say, submerged in oil or water? Would the forces between them get stronger, weaker? How does the stuff around them change the rules? That's a really interesting question, and a great topic for another time. Thanks for joining me.